Okay, so let's start then. Welcome everybody. Yeah, today it's my pleasure to invite Dr. Chirantan Chowdhury from University of Duisburg, Essen. He did his PhD with Professor Jochen Heinloth. Yeah, it's over to you, Chirantan.
First of all, thank you very much for the invitation. I will try to explain what I did in my thesis, and the title, as you have seen and from the abstract, is the Motivic homotopy theory of algebraic stacks. So as far as I have seen, this is kind of a number theoretic kind of seminar. So this has kind of nothing, almost it's kind of a disjoint thing, but it has a bit of algebraic geometry and everything. So I will try to give a motivation for quite some time and give some quite basic ideas of the tools, what goes on inside this, but there will be a lot of assumptions. So feel free to interrupt me of anything that you cannot understand. The main goal for me personally will be to give an idea of what this topic is all about and what kind of results I have got in a kind of a very not concretely, but just to give an idea of what this subject is. At first, before starting, as I said, I will try to motivate. So the whole idea of this, it relies on this what is called the six-functor formalism. So the six-functor formalism is kind of a formalism which was developed by Grothendieck to somehow understand cohomology theories and like all the duality theories, that what happens in algebraic geometry. So if one has to state what a six-functor formalism is, there are quite a number of definitions, but so it has to have like six functors. So what are these? So at first you consider functor F from some category of schemes. You can consider some nice category of schemes there. And you can consider, and it's a functor to a two category of all the categories, such that, okay, so it sends any x of your scheme to some f of x. And then you can consider there are like two functors here, which is one is called the pullback, this is upper star. It's the pullback functor, and we have the lower star, push forward functor for a morphism of schemes. And also you can actually also have this kind of exceptional functors, which we have this lower shriek and the upper shriek that we call. And these exceptional functors are not defined for all morphisms, but somehow they are defined for some classes of morphisms in this. So in typical cases, this is a separated of finite type. And so these are 1, 2, 3, and 4 functors. And then you have the rest two functors, which is a tensor product functor. That means you can like take two objects in your category and tensor them also inside your category. And you have also an internal norm. So these are the six functors, and the six-functor formalism states that, okay, we have these functors and there are some compatibility properties between all these functors. Namely, there is some projection formula, some localizations thing, which if time permits, I will try to say more. We have seen some bits of this things if you have encountered algebraic geometry, you have like smooth base change and proper base change theorems. These are kind of can be formalized and say that, okay, you have proper base change, smooth base change, you can say that there is an equivalence. There's a natural transformation between some composition of functors, and you want the natural transformation to be an equivalence. So that's kind of the vague idea of what the six-functor formalism is. Now, what's an example? So the first example that comes for which the theory was developed was the derived category of L-adic sheaves of a scheme. So this was to understand Ithal cohomology, so in particular to understand the Weyl conjectures. And so this was developed by Grothendieck, and all the formalisms were done by also like it was also done by Deligny and other people who have developed this theory, and they also constructed six functors and prove some comparative properties between them. The second example which is particularly the main interest of this talk, which I want to focus, is this Motivic homotopy theory of schemes. So which is done by Morel Voevodsky, where they developed this theory, and then all the six-functor formalisms were again proved by Ayub. So what is this Motivic homotopy theory of schemes? So this Motivic homotopy theory of schemes is to actually incorporate ideas of algebraic topology, namely homotopy theory, in the field of algebraic geometry. So you have in algebraic topology, we have this homotopy between parts, and you can understand how this topological space behaves up to homotopy. And somehow if such kind of correspondence can be done in the field of algebraic geometry, that would have been nice. And there is also, there's already kind of a stable homotopy theory in the field of topological spaces, namely what things are called spectra. And Morel and Voevodsky wanted to somehow incorporate that notion in the field of algebraic geometry. So that's what they did. What they did is, so the idea that, so what's the slogan is that Motivic homotopy theory should parameterize space of all cohomology theories over a scheme. All cohomology theories means here, I mean some kind of nice cohomology theories. That means it will be an object or a space, whatever you prefer, whose points are actually the presence cohomology theories, which you want to understand. And so it's a space where all the cohomology theories interact with each other. And how it is defined, at first I consider schemes which are Noetherian and a finite full dimension. And this Motivic homotopy theory is written as SH tensor. And this is a functor from two simplicial sets, which I am writing in the language of infinity categories. If you do not know infinity categories, just forget the things for the moment. Here you can just consider schemes. These are just schemes, it's a category of schemes. And here it's some target object, which is some category where objects are presentable. That means presentable here, it means that it has some finiteness condition. That means here objects are kind of like sheaves, which can be, so you know that every sheaf can be written as a filtered colimit of the presentable pre-sheaves, which is due to the Yoneda embedding and such axioms. So there is some presentable conditions in that sense. And it's called stable. So stable, if you don't understand what stable is, but you can understand. So you can just think it as a triangulated category. That means it has distinguished triangles, like derived category has distinguished triangles. And symmetric monoidal. The symmetric monoidal means there is a tensor structure there, which is commutative, associative, and everything. So you given any object X, you can consider such category which has all such nice properties. And how this is constructed, just to say in a very vague way, is that you consider some spectra of some kind of special kind of sheaves. So at first, so these are sheaves. So if I just have to explain here for some time. So at first you consider, so if you consider any X, you consider the category of smooth schemes over X. And you consider all the pre-sheaves of smooth schemes. So these are just pre-sheaves, these are just functors, of the contravariant functors. And then you want to consider not only just pre-sheaves, but some kind of species which has some special properties. Namely, the first property is that you want A1 invariance. So A1 invariance means that I want, if F is my pre-sheaf, then I want that F of X, F of Y is same as F of A1 times Y. That means if you change it by A1, it doesn't change. So this is somehow kind of saying in the analog of topological spaces that if you do it by delta 1 by interval, nothing changes. So algebraic geometric version of delta 1 is A1. So in a sense. So that's what A1 invariance does. And now I want to consider some other, not only just A1 invariant, but some kind of sheaves which has descent along some nice morphisms, which is this called the Nishnevich morphisms. So if you have not come across with Nishnevich, is because this doesn't usually appear if you are not in the field of Motivic homotopy theory. So what is a Nishnevich morphism? So if you have a morphism of schemes, I call them it to be Nishnevich. At first, I want it to be étal. So if it's étal, then you know that if you take any k point, then the field extension of your on the fibers, these are all just separable extensions of your residue fields. But now I not only want to be separable, but I want that one of the fibers, the field, the residue field is exactly equal. So that means you have a lifting of K points. So if you've taken a K point that exists a lift, that means over the fiber there is a one point where you can consider it to be not only just the field is separable, but it's exactly the respect K. And such a condition, somehow you can see that Nishnevich somehow lies between Ital and Zariski. So this is kind of a in between topology, which happens. That every Zariski morphism is, of course, it's kind of the nice morphisms that you want to have, like open immersions. But Ital is then, but Nishnevich comes in the middle. Now the question comes that why we want this topology? Like why will someone come across this? So why Nishnevich? Well, the motivation of why this Nishnevich comes, because it's named after a mathematician named Nishnevich who tried to prove some statements in K theory, and he defined this topology, and randomly all these conjectures in K theory were kind of true, and you can find you can prove some nice things. But to say in a brief way that cohomology theories that we are interested in, so which are like K theory, some algebraic cobordism, or Chow groups, or a variant of K theory, just called Hermitian K theory, this satisfies Nishnevich descent. That means these are, if you consider them as pre-sheaves, you can see that they do not satisfy descent along Ital morphism, but it's satisfy descent along Nishnevich morphisms. So if I consider Nishnevich descent, then I can consider all these objects as my examples in this SH, and I can study them, and I can understand how these things interact with each other. So that's why Nishnevich is kind of important. And of course, I didn't explain this P1 spectra thing. This P1 spectra thing is kind of like you take all these sheaves and you want to stabilize them. That means you do the kind of what you do, how you define spectra for topological spaces, that you take sequences of topological spaces and consider the suspension. You have like functors between the suspension of the one to the other, and you have morphisms. So you do kind of that similar kind of process, and you consider all these objects. So these are objects inside my SH of some scheme. So that's a very, very brief idea. If I have to describe this, then I have to go into detail. So that's a max I can try to say till the moment. Now, what are we interested in? So this is what the classical theory of six-functor formalism is, that on the level of schemes. But now of course, one loves abstractions. Okay, we have schemes here, algebraic stacks. Well, let's upgrade all of this there. Let's see what happens, what new things can we get. So to give a motivation of what is done already is that you can study what happens in the situation for derived categories for algebraic stacks. So if I consider X to be an algebraic stack, I hope everybody is kind of familiar what an algebraic stack is. If it is not, then I can just say that you can consider algebraic stack as a functor from schemes to groupoids, which is a sheaf with respect to some flat topology, namely, we consider this FBBF. And not only it is algebraic, what this algebraic means that you have a morphism from a scheme to this stack. So here the scheme is considered by the functor of points. So you have to consider the scheme as a functor of points. You have this analogy. So you have a morphism from a scheme to an algebraic stacks, which is smooth and surjective. That means that if I consider any other scheme mapping here, and I consider the fiber product of this, at first this should be a scheme, and this morphism of schemes is smooth and surjective. So that's a classical example of an algebraic stack, a classical definition of algebraic stack, and try to see examples are, well, to motivate algebraic stacks, you can consider like moduli space of elliptic curves, moduli space of vector bundles, classifying stacks of an algebraic group, of an algebraic group. You can consider all these examples. To study all these moduli functors, the language of algebraic stack has been incredibly useful since quite a long time due to the Mumford when they come across these definitions. So the naive definition, what can do, if I want to define this derived category, that okay, I want to define the derived category of L-adic sheaves over this X. So what I can do, I can define the derived category of L-adic sheaves over X. So I can consider this category, which is an abelian category. And given an abelian category, I can always define the derived category. That's how the derived category can be defined for any abelian category. But if I do that, I ran into kind of a problem. The problem is that if I consider the derived category of BGM, so where BGM means you somehow send your scheme T and you want to parameterize all the GM bundles, then derived category of BGM turns out to be derived category of all the GM equivariant L-adic sheaves over the point. This is because, this is somehow because of the fact that for BGM, the point is actually the atlas. So such a morphism is smooth and surjective. So there are some, so this is due to some fact of algebraic stacks that this happens. And this somehow gives you that as kind of GM is kind of a nice algebraic group, this gives you that it has to be the derived category of point. That means BGM and point are somehow the same, but this somehow doesn't work because already in the literature, the cohomology of BGM has been computed, especially due to Totaro, who shows that the cohomology of BGM should be actually a polynomial, a graded polynomial ring in degree 2. And this doesn't agree with the BGM of a point. So somehow this theory can be defined, but this is now kind of interesting. It somehow loses all the information. It doesn't see the difference between BGM and a point on a derived level. So well, this doesn't work. Then the next venture which comes along in this is due to Laszlo and Olson. So they use some simplicial methods to define such kind of derived categories. And I'm not going to define what they do, but what they do gives us the right definition. That means if you do these cohomological calculations, you get the correct one that you are hoping for. But there is a problem. What the problem is that if you want to define pullback functors now, so we don't want to just define this category, just derived category, we want to have the 6-functor formalism. So we want to have a pullback functor. And this pullback functor somehow is very technical to construct. This is because when they are trying to define, they use this kind of a new topos or kind of a new sheaves over a side, which is called the Lis et al. Topos. And this is not functorial. That means if you have morphism of algebraic stacks, you don't have a morphism between these topos, and somehow these are intricate to the definition of the derived category. So this doesn't work, and so they have to do kind of a bit of a technical procedure to construct such functors. So there is a problem in understanding on the functorial level what happens.
So one question.
Yes.
So you mean like technical, so they can't define it, or like
no, they can define it, but the thing is that it is a very intricate process to define it. Like it's not kind of obvious that what the functor is.
Okay.
That's the point. Means they actually, yeah, that's my, so what my, what the final statement is that they do, they can define, they have constructed 6-functor formalisms, but the pullback functor is not quite explicit, but like at least it's not obvious from the definition that this pullback functor should be like this. But
okay.
I was wondering something as well,
yes.
If I might interrupt.
Yeah, sure.
So I guess the difficulty is not necessarily, I mean, the difficulty lies in the definition of the derived category in the first place, right? Because it itself is a kind of diagram of derived categories, not really. So, I mean, I guess that can be addressed in a different way by using a better construction of the et al. Derived category, and then is that accurate, or I mean, I'm just asking out of curiosity.
Well, the problem is somehow it's somehow related that if you're considering the derived category as an ambient triangulated category, and the definition which they use is kind of a simplicial definition that's like taking limits over, taking some collection of sheaves over something, and you have to do this, and on a classical categorical level, this is not enough to define a pullback functor, that you somehow lose informations of quasi-isomorphisms because you cannot track quasi-isomorphisms in the classical derived category because they're already cancelled by the equivalences, by the localization.
So if you're considering just a diagram of stable infinity categories or something,
yes, then it works. That's what I'm trying to say in the next point. Yes.
Okay.
Yeah, thank you. So as what it is, as what I was trying to say, so in this construction, the pullback functor is technical, and somehow to get evade of this, Liu and Zheng, they come up with not just considering the ambient derived category, but to consider the infinity categorical version. That means this is just to say, this is a simplicial set. That means it's a functor from delta up to sets. And this is an infinity category. That means it has some lifting properties along some special simplicial sets. And so if you have such a simplicial set, I can actually consider its homotopy category. That means the ambient category which lies inside this, which is a derived category that we have. So you can actually enhance such thing. I can consider the infinity categorical version. And they use infinity categorical techniques which are developed by Lurie, and they also, and some other multi-simplicial definition to use such thing. Namely, if I can say what the definition or how one can see this. So if I consider an atlas of my algebraic stack, that means a smooth surjective morphism from a scheme, then this derived category can be considered as a limit over this chain of derived categories. So you have the class X, then you can consider its Weber product over itself over 3 times, then you have 3 maps and so on. So this is like a simplicial diagram of all the atlases, of all the n chains of atlases. And if you consider this diagram and consider all these derived category functors, and if you take this limit in the suitable infinity category, let's just say, then we get this derived category. And what's the advantage here with it comes is there that I know that if I want to define my pullback functors, then I can actually say, oh, yeah, on the level of each of my ambient categories, I have the pullback functors. Then if I take limit, then its limit is kind of a functorial association. So this pullback functor gets automatically associated with the functorial level to the limit.
Yes. Did you say take the limit over all atlases?
No, over a specific atlas.
But it's going to be independent of the atlas.
Yeah, that's what I was trying to say in the next point. So yeah, at first the question is, of course, why this is well defined, but it doesn't depend on the choice of an atlas. Actually, it is kind of independent, and this is because of the fact that on the level of schemes, this derived functor is an étale sheaf. So you use sheaf condition to show that like this is independent, and it doesn't depend on atlas. That means there is a more technical statement to see how one constructs this functor, but the core idea relies that it's an étale sheaf, and this somehow solves the problem. And as I said, the pullback functor, as a pullback functor also comes quite easier from this theory. And of course, this agrees with the definition given by Laszlo and Olson that they did, and on the level of homotopy categories. So that's kind of the vague idea of what happens in the setting of derived categories. Now our aim is to mimic this for Motivic homotopy theory. So the idea is to do the same thing for our functor SH, but there is a problem that SH is not an étale sheaf. It's a Nishnevich sheaf. This is, of course, you can see this because we have this Nishnevich theory. So this cannot be a Nishnevich sheaf. This cannot be an étale sheaf. So this is a Nishnevich sheaf. So it's kind of on a bigger set. And if I do the same definition, I take any arbitrary atlas and I do this limiting process, there is a dependency which arises because it's not étale anymore. And that's a possible, the possible way to get around to this, which we try to do, is actually define some subclass of algebraic stacks where this Nishnevich topology is kind of associated, and where we can do this in a kind of a similar way that it somehow doesn't depend on some choice of some specific atlases, not just arbitrary atlas. So a specific atlas that this algebraic stacks have. So that's what I'm going to explain in the more detail and somehow in some kind of detail. And this is what I call Nislock ST. And this somehow ends the motivation. Now the next section will be to somehow give a brief idea of what this Nislock ST is. So the first thing that I want to talk is morphisms admitting T local sections. So my setup is that I consider C to be a category and T some coverings, and C admits products and finite coproducts. So like C comma T is a site, then I define a morphism F from X to Y in C admits T local sections if there exists a covering of Y in curve of Y and morphisms Si from Yi to X, such that if I consider this disjoint limit Yi over Y over X, disjoint limit of Si and Pi, so these are Pi, this commutes. So just to interpret the definition, it says that T locally, it has sections. That means there exists a cover after which this morphism can be, there is a section of this morph. And example why one should consider that smooth surjective morphism of schemes admit sections étale locally. So a smooth morphism in this sense of definition has étale local sections, smooth surjective morphism. And you can see that one can see that these T local sections are stable under pullbacks and compositions. And this defines a new site called T-log, where I mean that the coverings of T-log of a scheme will be all this, these are all morphisms Yi to Y, such that this product Xi admits T local sections. And this corollary, so there's a corollary which says that that if there is a sheaf which is, okay, let's just write in C only, C of, which is an infinity sheaf with respect to tau, then fx to y morphism admitting T local sections implies that f satisfies descent along this morphism F. That means here maybe I should say something about this infinity sheaf, that what I mean in this kind of nice topology where we have these coverings and some finitary conditions, infinity sheaf means that if I consider like Yi to Y as a covering, then f of y, the sheaf condition boils down to saying that the f of y is same as considering this f of yi times f of yj over y, and so on. This is a sheaf condition. So in the usual one categorical sheaf condition, the limit somehow ends here. In the infinity categorical world, you take the limit over all the continuing Fabry products. And this means that f satisfies descent along f. That means that if it has descent along morphisms which are in my topology tau, it has also descent along morphisms in my topology tau log. So they're kind of the same. And I'm not going to explain the proof of this, but this is kind of an interesting thing of this topology. Now what we go into category of stack admitting T local sections. So this is somehow the thing, kind of a mechanism that we are trying to define this extension of the functor from schemes to algebraic stacks. So we want to work on some two categories, because algebraic stacks are actually two categories, because you have like two morphisms between them. And so that's a definition that we want to use, is that if I have a C tau site as before, then a category of stacks admitting T local sections is a 2-1 category, STC, together with an inclusion satisfying what? That at first it admits hyperproducts and small coproducts. Second, that if I have any object in STC, then there exists a morphism x to x, where x is in C, such that for all morphism T to x, where T is in C, the Fabry product is in C, and the base change morphism to T is a T local section. That means it is kind of the same definition of what an atlas of an algebraic stack is, but now there is some restrictions from topology, that this atlas is not only just a smooth surjection, but it is a T local section with respect to this topology T that I'm starting. And as I want something to be algebraic, then I consider that the diagonal is representable in C. So the diagonal being representable in C, that means this is actually a classical terminology saying that if I take any morphism from T, an object in C to the stack, then the Fabry product this is also in C. That means it's representable. That means after base change, you actually land in C. Well, in the similar way, we can actually define what does a morphism admitting T local sections in STC is. That means f and x to y is a morphism admitting T local sections if there exists an atlas admitting T local sections. So such a morphism X I actually call an atlas admitting the local sections. If there exists a morphism, if there exists an atlas and a map from Y to X such that just like this. Okay. So it's the exact kind of the same definition in the same flavor that we have for in the ambient category C. And you can actually now think that you can actually define T-lock topology on STC, and this forms a site. Right? You can define the coverings like this, and the set of coverings that you can show that this is a site because these are stable under pullbacks and compositions. Well, that's all the categorical machineries that one needs to have. Now let's go to defining this log ST that I just that I stated at the end of my motivation. The 2-1 category log ST. So how do I define this? So somehow, as you might have guessed, that I start with schemes and I start with Nishnevich topology that I want to consider. Then you can consider, if this is my C and tau, then I can consider my STC actually to be the category of all quasi-separated algebraic spaces. So this I didn't mention. So actually, when you're defining algebraic stacks, you somehow have to pass through in this midway object, which is called algebraic spaces. So in algebraic spaces is actually a functor to sets, and it is a sheaf, but it actually admits an étal covering. It actually admits a covering by a scheme, which is an étal map. So algebraic spaces are kind of the objects that one considers when considering group actions. So suppose if you have a scheme X and if you have a group scheme G acting on it, a final algebraic group, then if the group action is now like properly discontinuous and free and whatever, then this quotient exists as a scheme. But what happens if it is not properly discontinuous, but it is still free? So if it is still free, then you can consider this quotient, but this quotient doesn't exist in the category of schemes, but it exists in the category of algebraic spaces. And then now if you further remove the freeness condition and you want to consider just arbitrary group scheme acting on X, then this exists in the category of algebraic stacks, what we call as quotient stacks. So quasi-algebraic spaces, the algebraic spaces are kind of in the middle between algebraic stacks and schemes. So this one has to define this extension, one has to at first define it for algebraic spaces, and then one can move further to define it for the algebraic stacks that we are interested in. Well, for algebraic spaces, I can consider STC to be algebraic spaces. This is because of the fact that this is due to Knuston, that every quasi-separated algebraic space admits a Nishnevich cover. So you can consider such quasi-separated algebraic spaces, and they already have a Nishnevich cover. So this is a candidate that we can take as STC, which satisfies all these conditions. So yes, so let us denote this to be let us denote this category to be algebraic spaces. Then now I start with C, tau to be algebraic spaces, and I consider the Nishnevich topology there. Now I consider STC to be all such algebraic stacks which have an atlas admitting Nishnevich local sections. That means now I consider not all algebraic stacks, but all such algebraic stacks which admits an atlas which has this notion of Nishnevich local sections in the sense of STC. And this, atlas here, I also consider here to be smooth because I want it to be smooth also. And now this is my definition of Nislog ST. So this is my category Nislog ST. And well, okay, so that's the category, but why this is interesting? Like, are there nice examples that we can consider in this? Like, what's the, so corollary or local quotient stacks in Nislog ST. And so local quotient stacks means that it's an algebraic stack which has a covering by, which has a covering by open substacks, and each of these open substacks is a quotient stack. And why such these things are true? So let me just explain why it is true for X mod G. So here my G is a affine algebraic group. So as an affine algebraic group, it admits an embedding to GLN. Then one can see that X times G as a quotient stack can be written as X times, so you take the quotient X times GLN by G, and where G acts freely on this product space, and you quotient this by GLN. So if you compare these two quotient stacks, they are actually the same. And once they are the same, then what happens at first that for if my G is GLN, then the classical atlas X to X mod GLN is a GLN torsor. And GLN torsors are not only trivial étale locally, but they're trivial Zariski locally because these are special groups. So if they are Zariski locally, they're trivial, that means they admit sections. So of course they're trivial Nishnevich locally. So for special groups like GLN, the classical atlas will do the job. That's an atlas which admits sections Nishnevich locally. But now in this case, what I can do now, that okay, so if my X mod G is X times GLN, then you have X times GLN to X mod G, which is a GLN torsor now. And this is an algebraic space because this is a free quotient because G acts freely. So there exists another Nishnevich covering of this by a scheme because it's a quasi-separated, and that's what we use, that there exists another Nishnevich cover. So this composition is my atlas that I want to consider. So that works. So for BG, the point is not always the atlas that one wants to consider, but you can now change it to saying that I want to consider like GLN mod G, GLN mod, which when G is reductive, this is an affine scheme, that this quotient exists as a scheme. So this can be done. So that's true for all quotient stacks.
So one question again.
Yes.
So you mean to say that this atlas you are going to use what you said in the earlier also?
Yeah, that's how you show that these stacks are in this category. Yes.
Yeah. So, but this ultimately this will depend on this atlas, right? I mean.
Well, in the definition of the category, you do not say that the atlas is human. You say they exist. I want such an atlas to exist, such that this happens. So that's a well-defined definition by itself. That there can be multiple atlases, but there exists one, such that this category makes sense.
But is there any like other justification, like why this atlas works, or like, or
why this atlas works? This is one way of proving this, but you can also actually show at first that, like at first you show for like all the special groups, this is just obvious. And then you show that if you take an embedding from G to GLN, then you have an embedding from X mod G to X mod GLN. And this is representable, and you can show that if one is representable, then the other gets, if one is into category, the other gets also into category. So that's one way of proving this, but this is like more hands-on way of proving to show that you can actually construct one for this.
Okay.
Yeah. So in the similar way, you can now show that like moduli space of vector bundles, G bundles, X bundles, moduli space of stable curves. These are all in this Nislock ST. And this happens because of the fact that at first the moduli space of vector bundles and all these things are local quotient stacks. So they admit, and then G bundles then is some representability argument, and this moduli space of stable curves are, you can show that they are actually PGLN quotients by some PGLN action. So they are also quotient stacks. And these are somehow interesting in the field. So particularly the stable curves is a very interesting thing because that's a field of what people call enumerative geometry. That means you want to somehow understand intersection of curves with quadratic forms, and so you want to consider these moduli spaces, and to study some invariance on this enumerative geometry, one uses this. One needs to have. It will be nicer if we have a Motivic homotopy theoretic formalism for such stacks, and that's somehow kind of does the job. But okay, if it is calculatable or not, it's helpful or not, that's up for question. Well, so this is kind of the examples that I can say, and now I can say at least the first theorem that comes in my thesis is, okay, so this is extension. Sheets from schemes to algebraic stacks. So what is the theorem? So you start with a site, and STC is a category of stacks admitting T local sections. Let F from some number C up to D, the category, admitting limits, then F can be extended to Fx, which is a functor from this STC, which is an infinity sheaf with respect to the T-log topology. So here, well, so this is a nerve of a category which gives you an infinity category to a category. And here I'm using some symbolism, which is to associate how to functorially associate a 2-1 category and infinity category. So this is what people call Duskin nerve in the field of simplicial sets. But just forget this and just can consider that objects are just like stacks, and you map them. Moreover, which is the interesting thing, is that in particular, if you have an object in STC, and if you consider at last admitting T local sections, then Fx of x can be computed as a limit over the check nerve of x. That means that x of x is actually computed as a limit of well, so that's, as you can see from here, so this is kind of the similar statement that I stated for in the case of the derived category due to Liu and Zhang. And that's, but here we are not, as you say, that we are not somehow doing it for all algebraic stacks or something. We have some restrictions to some topology, this T. And that's one way of understanding what is this f of x is, to just have some remark that Liu and Zhang, so when they construct this derived category, the derived category construction uses what they call this descent program. So there's an algorithm where you input some objects, input some data, and you get some data out, like input some functors and you get some extension of some functors. And this is the way they extend this derived category functors. And the idea, so the statement is a special case of their statement in the descent program, but the proof uses new techniques, different from the proof in the descent. So the proof is kind of inspired, but the outline, the whole thing is a bit different from how they prove such results. And that's how it is done. Well, now let's just, if I have time, I will not have probably time. I can answer in the question session, maybe if somebody has, how this proof is done, or giving a brief idea. But let me just go back to how our stable homotopy functor is defined. So the corollary is now that SH tensor, which is from nerve of schemes of, at first we extend this to nerve of algebraic spaces, and then we extend it to nerve D of Nislov ST. And this functor, we call it to be SHX. So in order to do this business, we do this thing twice. Like we use this theorem and we use it twice. At first we extend from here to here, and then we extend it from here to here. And that's what SHX is. So what we get from this functorial description of this, that we not only get SHE of T of X, but we get 4 functors. Namely, for f of x to y, this functor sends to SHE of y to SHE of x. And this is my pullback functor that I want. And in this setting, I haven't explained this, I haven't stated this clearly anytime, that whenever in the language of infinity categories, when there is a powerful theorem between these presentable categories that you have an adjoint functor theorem, that if you have one functor which admits co-limits, then it admits a right adjoint. So there is a statement. So this functor, this L here symbolizes that all the functors here are co-limit preserving. And in the other way, it means that all these functors have right adjoint. That means as this functor F upper star lies inside this admits a right adjoint, which is this F lower star. And as my category, this SHE of X lies inside the symmetric monoidal structure, which was this C-alg, which is this commutative algebra objects. This means that we also get a tensor structure. And in the similar way, as tensor and Hom are dual to each other, you get Hom also. So you not only get you not only define this infinity category SHE of X, but we also get these 4 functors by free from this theorem. And now the main goal is to understand how these exceptional functors F lower Schrick and F upper Schrick are defined. Well, this I'm not going to state much about it, because this is the kind of the most technical, very more technical part of this whole construction business. But we can define it like, if F from X to Y is a representable morphism of algebraic stacks in this log ST, separated and finite type. So you can define between representable morphisms, what do you mean by separated and finite type? And for those, we have these F lower Schrick functors from SH of X to SHEXT of Y, and we have the upper Schrick functors. We have only for representable morphisms. And such this, we also have a projection formula. So projection formula shows that if you have like F from X to Y, which is representable, separated, and finite type, then at first you can consider like F so F lower Schrick of some object E, tensor E prime, and you can consider tensor E. So this is kind of a projection formula statement that, okay, so where E is in SH EXT of X, E prime is in SH EXT of Y. So we have kind of an equivalence between such objects, and this is also comes in the language of derived categories also, that we have such kind of statement, and we have base change statement also. So this is where I will end. So we have X prime, Y prime, X and Y, which is Cartesian, such that these are the presentable separated or finite type. So this is G prime, F prime. Then you have a natural transformation. So you have SH EXT of X going to upper star of SH EXT of Y, but you have the lower Schrick map here, Y prime, SH EXT of X prime, F prime upper star, and you have G prime dot Schrick, and this comes. So this is kind of the base change statement that you also have. And yeah, so this is kind of the two major things that one has, and we have also other properties like localization and some other kind of things which are called homotopy purity, which is like analogous of shared duality in the language of Motivic homotopy theory. And all these things uses the tool is to use what people call the enhanced operation map, which is due to you and so on. Yeah, that's all I wanted to say on this, and that also concludes the talk. Thank you for your attention.
Thanks. Okay, thanks for the nice talk. Yeah, so are there any questions from the audience?
I have a few questions. I might.
Yeah.
One kind of just a meta question regarding the literatures. What I don't. I'm sorry. Forgive me if I missed this. But what's the relationship of your formalism with the sort of that of Khan and Ravi, for instance?
Oh, okay. Okay, that I didn't state anything here, but there is. So what Khan and Ravi have done is like they defined like this that SH. They define this for any derived stack, or in my case, I will restrict to just algebraic stack. They have defined this SH delta of X to be limit of like SH of X, where X is a smooth morphism. And they have taken limits over all such covers. And there is a corollary that is mentioned in my archive article and also in their paper of Khan and Ravi, that if my X is log ST, then we have a canonical functor from SH delta to SH EX, and this is an equivalence. So if my stack is if we consider the stacks that we have, then like considering, so in their definition, this kind of works. So you do not see the independence of a class is not there. But if you want to do some calculation business, then this is like a huge limit. And this is just a lot of objects to consider. But whereas if I have this like check nerve kind of a description, this gets like quite intricate and quite easy to understand on a specific class that I need to understand. So it gets more hands-on for the calculation business. But of course, if you want to see this independence business, then you can use the definition of Khan and Ravi and see, okay, this is just, there is nothing to prove there. But of course, one has to show why this is a factorial association and why everything works. But if you know the language of Khan extensions, then this is quite clear that this can be done.
Yeah. I was also wondering, you mentioned the potential applications for enumerative geometry. Is there a kind of program on developing kind of Motivic Gromov-Witten invariants or Motivic categorified Gromov-Witten invariants, something like that?
Well, to understand invariants on these things are still work in progress, because the thing is that one somehow uses these lower Schwick functors that one needs to understand for understanding like virtual fundamental classes of this. But if you want to understand like on like field, then you have to have some notion of lower Schwick for non-representable morphisms. And because like from your algebraic stack to ground field, this is always non-representable. And we don't have lower Schwick for non-representable morphisms. So that's a work. Whereas there are some notions of non-representability, but these are kind of questioned because in the language of algebraic stacks, there is no good notion of separated morphism because there are like various notions one can see what we want. In the representable case, everything works, but in non-representable case, if you want to have like a BGM to K to be BGM stack to be separated or proper, because this is topologically CP infinity. But if you want to consider the structure morphism and if you want to show that, okay, I want to have the diagonal to be closed and whatever, but you don't get closed. So you're somehow confused at what's going on there. So you don't get the nation. So one can define by just saying that you can define by evaluative criteria, but the question is that whether this is enough or not, or what can be done. So for the moment in my thesis, I didn't do anything for non-representable situation, but there are procedures to do this, but I'm not sure like where you get, like what information can you get from this. That's all I can say in this business.
Any more questions? I actually have a question which maybe doesn't make that much sense since I don't understand that much. So like how general this has, like, let's say the applications for example, let me ask a specific paper. It's I think a recent paper by Weinstein, David Hansen and Daniel.
I know. Mm-hmm.
Okay, so they also developed the six functor
Yes.
formalism for diamonds and V-stacks.
For V-stacks,
they
yes.
But they also use this Liu Zhang, this enhanced operation map. So like, can you also somehow use your theory on this V-stacks and diamonds?
Yeah, well, of course, this, as I said, that this enhanced operation map I'm also using from what Liu and Zhang is doing. But of course, there is this can be used in the language of V-stacks, like, or like, for example, if people are familiar with that, in the context of Motivic homotopy theory, a couple of, like, Ayub has been working on rigid motives, rigid analytic motives, like on rigid spaces. He has notions, and like 2 years ago, like they also came with a 6-functor formalism on rigid motives. Ayub and some couple of people. So one can now think that, okay, now one can extend this to rigid analytic stacks in a way, and can understand this. But yeah, of course, the question comes, is this interesting enough? Like, what can you do there? Like studying Motivic things on the setting of rigid, on the stacky level, in the rigid, I guess in the schematic level, we have these things called nearby cycle functors. This gets somehow interesting in this rigid setting. But in the stacky level, this is quite confusing. But technically, what Weinstein and Hansen they did is exactly the same thing. That they actually wanted something for non-representable. That was the idea. Like, if you look closely, Scholze, in his paper of Ital cohomology of diamonds, he has this functor formalism, but he has this logic only for representable morphisms.
Yeah, like quasi-finiteness.
Yeah, quasi-finite. But then now they want it for non-representable, and that's the enhanced operation map can be done for non-representable morphisms. But the question comes because in the rigid setting, things get very kind of easier, in the sense that in the rigid context of rigid geometry, when you're defining lower Schrick, so when you want to define it for some compactifiable morphisms, you have a canonical compactification.
Okay.
So even between morphism of rigid schemes, you have a canonical compactification. In the setting of schemes, we have this classical Nagata compactification that people say that you have an open immersion, but this is classically non-canonical.
Okay.
So one has to work a lot here to show that this somehow doesn't depend on compactification. That's what Deligny did in his paper, where he does this, proves this lower Schrick and constructs this. That he has to show some, like, if you take two compactification, then you can take a bigger compactification and can choose one and the other. And taking limit over all of this makes sense. But in the infinity categorical level, this gets even more crazier, because there was just derived category, it was a 2-category thing. But in infinity category, you have to like coherences and coherences and this. And that was the first paper of Liu and Zhang, where they try to somehow make a formalized statement generalizing the Deligny's proof in infinity setup, which uses quite a lot of intricate techniques. And the paper is quite a thing to be read, let's just say that. And so that's what they use, and that's what then they use these techniques to do this enhanced operation business also. So there's a lot of intricate business there which goes into this. But in the rigid setup, things get a bit easier, but maybe now with condensed formalism, things can be connected. Let's just say that also, that you can pass from discrete adic spaces you can consider a scheme as a discrete adic space, and that's how they manage to do this coherent duality with condensed stuff also. So there are a lot of directions one can see this, but we have to see like what's the right setup can be done.
No, I asked this because there is another kind of an interesting stack which has been becoming quite popular in, like it's called Emerton G stack. I mean, it's also so. I guess my next question would be whether one can also get this enhanced fixed functor formalism for this Emerton G stack also. Right? I mean,
but this, the Emerton G stack is a specific stack, right? Or is this like
exactly.
functors? So you can, I do not know if it lands in this V stack or all these things. I personally haven't studied Emerton G stack. I just know what V stacks are, or a bit of this because I was looking. So if these stacks are already there, then like as Hansen and Weinstein stuffs can be applied and see like what this stack gives. But as I said, at the end, this will be a limit over some check nerve, over some nice atlas. So in the casing of a V stack also, you can cover it by a diamond. Like that's what those things is doing. So V stack has a representation by a diamond. So you use the Schulz's formalism for diamonds that you have that, then you extend this for V stack. So you take the limit of all your derived categories over diamonds, over the check nerve, and that will be your, if you want to understand. So an object here, an object in this limit will be a collection of all objects in each of these categories with equivalences when one object is pulled back to the other, and higher data between these equivalences. It's very hard to explicitly write what an object here is. Because that's what I can say.
Okay, thanks.
I just realized we didn't really talk about.
Yes.
I just realized we didn't really talk about interesting cohomology theories.
Yes.
But I mean, for stacks in this context. But skipping over that, I'm wondering if you have, again, forgive me if I missed this, if you have a representability for algebraic theory for your stable homotopy category or something like that.
Well,
something that reproduces the classical statement.
Well, if I want to see, so that's the first question comes, what are the homology theories in this SH-EXT of X that one can study? So the first thing that one can study is, one can come is Motivic homology or Chow groups that one can try to understand. So, well, Chow groups are fairly studied for algebraic stacks due to Crash and Totaro and everybody. And if you look into this paper of Adil and Charania, where they define this, they actually have this thing that if you have your stack admits a stratification like a Borel approximation, then you can compute this Motivic homology as taking limits over everything, over all these covers. And if you do this for the Chow groups, then you can get a hypercohomology of the block cycle complex, actually. And this actually gives you that the Chow groups here actually agree with Kresh's Chow groups, not only rationally, but also integrally. Because you are not, Adil's previous paper on virtual fundamental classes has this SH et al. Thing, where Chow groups agreed rationally because it was et al. But now it agrees, I believe, means it's not written anywhere, but if I combine my theory with what they did, and if you put 2 and 2 together, then it seems like the Chow groups will agree. Well, now the question comes for K theory. Well, the K theory can be defined in some way, but what kind of K theory it is? Is it the naive one, or is it the Atiyah-Siegel completion, like the completed version? Is it some other? That's a question, because that's a question which I'm also I'm trying to also understand, but it's still not clear yet to me. One can define stuff, but like one can define stuff, but I'm not clear. Like what can be said in this limit level? Like what is the K theory spectrum?
So this algebraic K theory of a stack, in this case, could be algebraic K theory of its derived category. or something like that. And then, I mean, in complete homology.
Yeah, the completed means if I want to see the K2D as a Motivic spectrum there, then one can consider the K2D spectrums over all these atlases and take this limit, kind of a thing. Okay, and this is an object. But what is this? Like, what are its homotopy groups? Are these the completed ones? I don't know. I have no idea, because it's kind of a Mittag-Leffler thing which happening there. Yeah. And it's not. It's also not. It's not coming from this genuine homology theories, or which can be written as like mapping spectrum between something and something. Like K theory is just PGL, and so that's the thing which still is in question, I would say. That's same follows for Hermitian and other things. So.
Okay, thank you.
Yeah, thanks.
Any further questions, comments? If not, then let's thank the speaker again. Yeah, and then I guess we'll close the session. Yeah. Okay. Thanks, Chirantan.
Thank you.
Thank you, Chirantan. Thanks.
Yeah. Yeah. Okay.
So
bye.
I think the next session might be in 4 weeks, because in 2 weeks we have an Iranian holiday. So
okay.
So see you all in 4 weeks.
See you later. Yeah. Bye.